So we will continue with our design of a workable system. So we learned a little bit about design of workable system through an example. The example was the pump and piping system, okay, which you all designed, and each of you must have got a different answer, hopefully. I mean, so there will be several pumps which could satisfy the same job, or each of which may not be desirable if you decide on a criterion of desirability. What is desirable? For example, if you want a minimum total cost, then you will have to do an optimization. That is what I mentioned in one of the earlier classes. So if you consider this example, you have now designed a workable system. Now we will formally see what a workable system is. So what are the features of a workable system? So a workable system is one which no, make it more satisfies our performance requirement. In this case it should be able to pump the water, correct, satisfies our is that all? If it satisfies your performance requirements, it's okay. Huh? Cost what? Right now I don't know whether it is the cheapest or whatever, but you can still say something about the cost.
Should be economically viable.
Okay, so we should have reasonable cost. For example, in the problem which we worked out, had you taken a 6 millimeter diameter pipe, which is a quarter-inch pipe, you could have come out with an answer where the horsepower rating of the pump was 15 or 20. Immediately you would have realized that even though this pump will also technically do the job, there is something fundamentally incorrect about your value of the diameter which you assumed in the first place. You will turn around and try to correct it. You are getting the point? Therefore, even though several designs may work, all these may not be workable systems, not because they do not satisfy our performance requirements, they do not satisfy our criterion of a reasonable cost. Reasonable cost is basically it cannot be taught. You can't have a course on what is the reason. So I think all of us will know. For this case, if you have a pump and piping system which costs between 5,000 and 10,000 rupees, 15,000 rupees, it's all right. Suppose if something costs 75,000 rupees, 1 lakh or whatever, you know that something is going wrong. Okay, so some of the fundamental dimensions which you have assumed are not correct. Therefore, should have reasonable cost, and this cost can the cost basically consists of two components. What are the two components? In something like a pump which is running, fixed cost. This is running cost and maintenance also included, okay. Running cost is the cost of power, and both of this should be reasonable. Is that all? If a system satisfies these two criteria, does it become a workable system? We are almost there, but not yet. Are there some more conditions which the workable system has to satisfy, which the system has to satisfy? It should satisfy all our constraints. The constraints could be in the form of pressure, temperature, pollution guidelines, and material properties, correct. The constraint could be in the form of, finally, for example, now asbestos is banned, right. We cannot use asbestos, okay. So you may come out with a system which is fine, which satisfies our performance requirement, okay, which for example you are trying to come out with a design of an insulation system with asbestos, it will satisfy these two, but it will cup when it comes to satisfying some guideline, some regulation which is in place when it violates, okay. Therefore it should satisfy What are these constraints? Example, temperature, and so on. So in trying to define the workable system, I deviated from the normal procedure. So first we designed the workable system and then I formally defined it. So it's little more interesting. The conventional way of teaching is first I will tell you a workable system is one in which all this, and then I will say now let us do an example. Let us design a pump and piping system. Just to have some fun, little bit of change. We first did the example and then I don't know whether this works better than that or there is no way of proving it. Okay. Of course, after the class you can tell me whether it's okay or not. Now, how did you design this workable system? Now that you have designed one, now that you also know what are the attributes, what are the characteristics of a workable system, when you did this, when you carried out this design of a workable system, how did you go about doing this? What are the steps involved? Okay, first you requirement is given. Can you be more specific? What did you first choose? No, you're not getting. You're getting too specific. More conceptual. Even before that. Not time. All these you. More primordial, more fundamental than all this. First you selected the concept, right? It may sound silly, but every day you can hire somebody, pay him money and give them 2 or 3 buckets and ask them to fill up. No, technically that's also a solution. They can go and fill up. They will climb the stairs and pour the water, take buckets full of water, and that is also. So you decided that there should be a centrifugal pump or a jet pump, whatever, and there will be a piping and pump. There will be a piping and pump arrangement which will do this job. Select the concept and then you went about fixing the pertinent parameters, right? You fix certain parameters. For example, in this case you fix the diameter and you perform the calculations. And then not choose. Choose the nearest available what pump. What is it? Product, is it? Whatever. Solution. Okay. Good. Okay. So if you get something like 3.264 kilowatts or something, you will choose something like, if 3.5 kilowatt is available, otherwise you go for 4 kilowatts. Or normally outside still they follow the HP system. Okay. Even in cars we still talk about HP, we don't talk about kilowatts. Okay. So they will be available in multiples of watt in horsepower. So it will be 1 horsepower, 1.5, 2, 3, 4, 5. So you round it off to the nearest horsepower motor and then decide that this is the solution, right? Now this basically essentially gives you an overview of how you go about designing a simple system. Of course, if you have to design a complex system, you will have to do complex calculations. You may write a program yourself or you may take recourse to using commercially available software, whether it is CFX, Fluent, ANSYS or what have you, right. But now the actual story starts. Each of you has come out with a particular design, but all of these are not equally desirable. When I say all of these are not equally desirable, I am getting more specific. So, I am introducing what is called an objective function. What is my objective? So, the objective function is mathematically denoted by y. Now, I have to say what y is. So, for example, in a project like this or in a problem like this, the y is very straightforward. The y is basically the cost. However, I told you in social projects what this y is very nebulous, and cloudy. You do not know what y is. For example, you build a flyover, what is the objective function? Whether the flyover has eased the traffic problem. Okay, it could be at several levels. The users subjectively will say yes or no, or you go through a survey and find out whether they are happy, or the traffic engineering division of a civil engineering department of IIT or Anna University may actually commission a study. At the end of 1 year, they find out what is the average time taken by vehicles to cross Raj Bhavan to Madhya Kailash, how much time they have taken before the bridge was constructed and after the flyover was constructed, and you can give some numbers, right. Therefore, please do not assume that the agreement on what y is or the objective function is trivial and straightforward. Oftentimes the definition of this objective function is not so straightforward. So, it requires a lot of time and effort. For example, if you want to design a heat exchanger, it is not that it is always that you want a minimum cost, okay, because you can have a minimum cost heat exchanger which has terrific pumping power. So, shall we say that you want to have a maximum thermal performance divided by the pumping power, the ratio of the heat transfer rate divided by pumping power, pressure drop, Q by delta P. Is it a performance criterion? Or you can really go to the bottom of it and say that I want to design a heat exchanger which generates the least total entropy. But what is the use of generating? Who cares about entropy? Let me generate little more entropy. See, when I speak, I am generating entropy. Who cares about that? Then some guys, the pure thermodynamicists will say no, we can link up this minimum entropy generation with actually the rate of heat transfer divided by pressure drop and all that. You know Professor Bejan, who is very of heat Duke University, Durham, North Carolina, has done a lot of work. So, you are encouraged to read his books and articles on entropy generation, how the entropy generation method can be used for designing thermal equipment. That is a separate story. So, there need not be a consensus on what the objective function is. So, it is left to the analyst. You decide what is your objective function, go about minimizing or maximizing the y. Now, what could be the objective function in this case? Now, let me ask you a very direct and pointed question instead of beating around the bush. How do you optimize a system under question? First and foremost, we agree on what is to be optimized. In this pump and piping system, what is to be optimized? Cost of installation running, that is enough? Cost of installation means be more specific, you are getting there. So, there is a cost of the pump, one, then there is a cost of the piping, then there is a cost of installing all this, then there is a cost of labor, all that is fine, then there is a cost after you switch on, maintenance and running cost. So, the objective function now, or we say objective, minimize the lifetime total cost of this system, right. So that is a fair objective, right. Now we will have to enumerate the various components which constitute this lifetime total cost and try to see whether we can write down all these costs in terms of some numbers, in terms of some equations. Then you have to assign values to the various values to the various constants available in your equations, and then use an optimization technique of your choice and find out what are the optimum operating conditions for the system under question. Okay. So that is the story. So we will just cost involved. I will say first cost of pump. First cost of pipe. Okay, I am including and fitting. This is not central to this, but lifetime that means pressure drop and all that. I can put into some 1.2x or 1.3x to take care of the maintenance and all that, so that the problem is tractable and handleable. We can keep on complicating the problem, okay, but for a classroom environment we have to stop it at a certain stage. Now, is it possible for us to write all these costs in terms of the fundamental quantities which are involved in this problem? The fundamental dependent variable in this problem is the delta P, or the pressure rise. Now we turn around and try to write down mathematical equations for all of this, each of these costs in terms of delta P. We will do that. Let us start with first cost of pump. Okay. The cost is proportional to because delta P. Why? Yeah, it is proportional to delta P, it is also proportional to the volumetric flow rate Q, but the volumetric flow rate is fixed in this problem, so that does not enter the problem. Therefore I can say pump cost how do you get A and B? It cannot be given in textbooks. A and B depends on local conditions. A and B may change in Ahmedabad, it may be different in Madras, it may be different in New York or whatever. Local conditions will apply, okay, to decide A and B. A and B can be easily obtained. You have to just go to a hardware shop, give me 1 horsepower to 10 horsepower, give me the cost, come down, put it on Excel and get A and B, which you are going to do, assignment number 2, it is there already, okay. So you will go to Velachery or Taramani or Google, whatever, you will get A and B, done. Now let us do the other cost. I am going from the simplest to the more difficult to the difficult. So I will defer this, I will defer this to the end. Let us go to lifetime running cost. So the cost is proportional to the energy consumed, right? So the energy consumed is proportional to the power into, correct. Assuming that the performance of the machine does not deteriorate with time, to the extent that the time required for operating the pump changes, it is a fair assumption that the time need not be considered as a variable in the problem. Therefore, the cost is proportional to the power. Again the power is proportional to delta, because power equal to so if you assume that the efficiency is constant over this period, if you assume that the discharge is constant, it is proportional to delta P. Therefore, the cost, lifetime cost you can get C and D, right? Can you get C and D? What all you need to know for C and D? Cost of electricity. It is not so. Sometimes what happens is, suppose you are working on a project and the project is supposed to work for 15 or 20 years, then you have to consider inflation into account. The cost of electricity is never constant, it changes. So a fair assumption would be last 5 years you look at the trend and then assume the average inflation rate and then factor in the inflation. It will be, this year it will be 1, next year it will be 1 plus x, there will be 1 plus x into 1 plus x. It will go as a GP, it will go as a GP. Okay, so things get complicated. Now you are trying to design and optimize a power plant. Just like these costs are going up, the revenue will also keep changing with inflation, and that is one thing. And you got money from somebody and you are paying interest for that, and this will be basically diminishing balance. At the end of every year you would have paid a certain part of the principal. So slowly it becomes very difficult. So you require a large program to run this. Okay, but for the classroom environment we will stick to this story, but I just want you to appreciate that it could get really messy. So we have got two costs. Now how to get the cost of the pipe? Cost of the pipe is directly proportional to the length. No, weight. Yeah, that's a good. So mass, assuming that it is operating under 1g. So assuming that it is operating under 1g, you can say that the cost is proportional to the weight. The length is pretty much fixed here, right? Because you know what is the length and how many bends are there and all that. So the weight is equal to pi d t L, correct? Pi d t L, where t is the thickness, d is the diameter and L is the length. Assuming that we are not going to have designs varying from 1 HP to 200 HP, if t is considered more or less constant, which is a questionable assumption, but I am allowed to do all these assumptions. So if t is maintained constant and L is maintained constant, the cost is directly proportional to the diameter. It does not help me how is the diameter related to the pressure drop. Take 5 minutes and get a relationship between the diameter and the pressure drop for turbulent flow. Cost is proportional to diameter. What is the relationship between the diameter and the pressure drop? Why? Because I wrote the other two costs already in terms of delta P. If I write the third cost in terms of delta P, now I have formulated the optimization problem where the whole thing is a function only of delta P. I go attack this problem and get the optimum delta P so that the cost is minimized. Inversely proportional. I am asking you d to the power of what? It is not such a straightforward problem. You have to use FLV squared by 2 GD, all that. You have to use all your knowledge of fluid mechanics to get this. There is a friction factor. Friction factor has a diameter, because 0.182 Reynolds to the power of minus 0.2. Then there is a 4 FLV squared by 2 GD. V is the velocity. M is equal to rho A V. A is pi d squared by 4. So d comes so don't be lazy. Get going. Okay. That pi dt, how we got that, I don't have to explain, right? There is an assumption involved in that pi dt, isn't it? So pi by 4 d out whole square minus d in whole square, d out, do a Taylor series expansion and all that. Okay. What is this d now? There are other d's now in that. There is a di, there is a do, some average. So I think these guys, normally it is called as the nominal diameter, right? It's called as nominal diameter, but the nominal diameter will not be the average. Has anybody worried about this or thought about this? The norm, it will not be exactly equal to the mathematical average of the inner and outer mean. It is based on something. Okay, suffice to say that d is the nominal, is the average diameter. Then we proceed. Now delta p dash, delta p will be equal to delta p dash plus static head loss. Delta p dash itself, okay. Now we do not know the V directly because we have specified only the mass flow rate. No. Is it okay? Is it okay? Correct? So, you are not done yet because f is also a function of Reynolds number. Of course, if you are a practicing engineer, you may we neglect it, and but we want to get to the bottom of the problem, so we might as well do it, right? One more step. Assuming that the flow is turbulent, you guys are able to see this? So that is a problem, huh? You are able to see up to this? Okay, so from next class onwards I will. Alright, so f is So now we have to do the, so F is okay, therefore okay. E to the power of minus 4.8. Is it minus? Is it plus? Huh? Not minus 4.8.
Correct.
Okay. Now, so we have now see when you look at, so when you do design and optimization, when you do a design followed by an optimization, the problems will be like this. Nobody will tell you from a textbook take 4 meters per second of 4 kgs of water flowing in a tube on 1 inch in diameter and this thing calculate. That is textbook learning. So now what you have to, so we don't have anything, everything is in the air. Now slowly we start writing everything, and whatever you learn from fluid mechanics and heat transfer and all this you are incorporating and then coming out with the design and then trying to optimize. Real life problems will be like this. Okay. Analysis is only one part of the story. Unfortunately in all the courses we teach you only analysis, because we believe that if you are strong in analysis, eventually you will be good at design. Design is basically synthesis, the synthesis of several concepts, several ideas. Okay. Now total cost. F plus so now we have written the total cost in terms of delta P. Delta P is the pressure rise which is taking place in the system. That pressure rise is a variable which is under your control. Okay. So if for different values of delta P, the total cost goes up with delta P. If you look at term number 2 on the right hand side, the term number 3 goes down with delta P, because there is one term which increases with delta P and there is it's immediately followed by another term which decreases with delta P. There is hope for us to optimize. There should be a particular value of delta P at which the total cost will be extremized, that is it will be stationary, but we really do not know whether this will be the maximum or minimum cost. But after doing all this, intuitively you can guess that it will be the minimum cost. However, as a purist, as a mathematician, you are not able to appreciate this, go ahead and take the second derivative and evaluate it. For engineers, I don't know, if you try to optimize the total cost of a power plant, you put all these factors into account and then get all these numbers, have a complicated optimization program running and finally get your final answer. Why would it be the maximum cost of the power plant? But the mathematician, no, second derivative. Okay, so if it is more than this thing, we will evaluate the Hessian, we will prove it is positive, definite, semi definite, whatever you want, we will do it. But as an engineer, I am convinced that already I have got the answer. We have written on the board, now we will formally solve this optimization problem. Okay, so this will be the assignment number 2. So the submission date is 26th August. So the problem reads like this. So there is an overhead tank of a big apartment. I have given a capacity of 15,000 liters. It is desired to select a pump and piping system to transport water from the sump to the tank. Distance is 300 meters. Tank is at level 25 meters above the sump. Okay, so 25 meters about 3 stories or whatever. For operational convenience, the time to fill the tank shall be 100 minutes. Losses in expansion, contraction, bends and elbows have to be calculated appropriately. You have to get all this kV squared by 2J. K you can get from basic fluid mechanics textbooks. Okay, and then design a workable system for the above and sketch the layout. That is a part 1 of the story. You design a workable system and on a A4 sheet you do. And now using data for PVC GI pipes from local market sources, it could be anywhere, or from Google, assign realistic values for the pump efficiency, cost of the pipe and pump and running cost including maintenance cost. With the help of any method known to you, obtain the value of delta P developed by the pump at which the total cost will be a minimum. The pump is expected to work every day and the daily consumption is 30,000 liters. Capacity is 15,000 liters and it takes 100 minutes to fill. The cost of electricity may be assumed to be 5 per unit and increases by X% every year. The life of the system may be assumed to be 15 years. Odd roll numbers we will work it out for PVC and X is 4%. Okay, even roll numbers we will work it out for GI pipe and X is equal to 6%, so that at least I have 2 copies. Okay, so it cannot be only one. So we need 2 original designs. Okay, so so you can talk to each other and group work and all that, but you should not submit the same thing. Suppose you are submitting a script, you will submit your script, MATLAB script and this thing, at least change a few variables and otherwise I need to have an oral exam which will involve time, and this is what is done in Germany. For example, the end semester examination is oral exam, you know that? In Germany the end sem at fluid mechanics the professor will have 4 books. Okay, so in order to ensure that it is fair, you will call these 3 PhD students who will be sitting. Okay, the exam will be, you will take boundary layer theory by Schlichting. Okay, boundary layer theory 400 page, explain this. Then he will directly say no, you are failing, come next time. That is it, you cannot argue this thing, retotaling, re-evaluation, nothing. The professor is supreme, so he says no, you will fail, please go back, come after 6 months. Okay, we are somehow obsessed with this written exams and all that. Okay, output expected, setting up of the optimization problem with data, sample calculations, you have to show plots, final configuration and sketch. Electronic submissions are unacceptable, but if you want me to take a look at it after submitting the hard copy, you can meet me in my office. If you have got something interesting or something, or you solved using a different technique instead of just plotting and looking at the graphical variation. If you have hit upon some other idea and you want to discuss with me or this thing, it's fine. Is it okay?